Hi friends, this video is going to be part of a series where I explore different topics that you might want to know about when you're building your first game on the web. Specifically, I'm going to share a stream I did where I explore different aspects of Mainloops, talking about maximum FPS, doing frame rate limiting, doing frame interpolation, and all of those kinds of things, and reasons why you may or may not want some of these things. So let's get into it. I wanted to thank my sponsors. Big help there. And if you'd like to be a sponsor, you can check me out on GitHub Sponsors or Patreon. We're going to talk about Mainloops. The plan is to go pretty deep into Mainloops and kind of explore all the bits in there. Kind of a core pattern. Figured it was a good place to start. I'm wanting to do a series here on topics that are useful for web game dev. So Mainloops are kind of like the core nugget, and there's a couple of really kind of nuanced things. Especially as you're getting into like limiting FPS, time-based movement, doing fixed updates, even interpolation. So those are some interesting topics that we can dive into. I've posted the code in the chat, so if you wanna go and take a look at the code, ahead of me, you can go right ahead. I've done a little bit of setup ahead of time, just to get things bootstrapped, so we don't have to build everything from scratch, and just so that we can get right into the meat of it. But I think first thing on my list is, what is even a main loop? What are they? I think there's a really great book here by Bob Nystrom. It's available for free on the web, but he has a passage in here about game loops. But it's effectively an infinite loop that continuously runs, collecting input, commands, and updating your game and drawing your game. So, it really is as simple as it's an infinite loop that processes input, updates the game, and draws it. There's in the old days, you didn't you would know like the hardware specifications, so like how long you had between draws in like a Nintendo, and that's how you would do your arithmetic of how fast your characters move on the screen. We'll talk about that a little bit. It's a way of doing games. A lot of like interactive games like run, jump, those kind of things might be well suited to this. There are certainly games where you maybe don't need this, but I'd say a majority of games use a main loop, also called a game loop here in this post. So I really do recommend checking out this post, and a lot of what we're going to talk about today is in this post. In fact, like there's a lot of nuance here. A lot of the things that I'm going to be talking about today are in this post, so I really do recommend checking it out. So game loops, what are they? What are they even? They are an infinite loop. So we're gonna make an infinite loop in the browser. So it's not as easy in the browser as doing like a while true, if only. There's a couple ways you could do it. There was the old school way, which was you either use a set timeout or set interval, and we can pull up those. Just a little brief history here. So, we can look at set timeout or let's look at set interval. In set interval, what it let you do is you could specify some code and tell it what interval you want it to run on. So, for example, if you wanted like a 60 FPS game, you would say, okay, I want you to run my game loop, which is a function, and I want you to run it every 16 milliseconds. So if we did the math here, 60 frames per second, right, is 60 frames over second. That we can do the math to figure out how many milliseconds that is. So you could inverse it and divide it by 1,000, which is just 1,000 over 60, and that'll get you the milliseconds. So 16 milliseconds, 0.6 repeating. So that'll get you. So if you're ever like, oh, how do I figure out how many milliseconds is for a particular FPS? So say you have 30 FPS. Okay, that's actually a really convenient one. That's how you have 33 seconds. If you had say you had 5 FPS, that's 200 milliseconds per update. So that's kind of the idea there, per FPS. So the old way was set interval, and that kind of sucked because set interval doesn't really give you any guarantees about when it's going to run. Enter HTML5 request animation frame, which is the new old hotness. But request animation frame syncs up with your screen. So it knows when your vsync is running on your browser, and it knows when to call you back so that you can paint with the screen, versus set interval, you might paint whenever, and you might miss a screen update. You might update twice in a screen update, which doesn't do you any good to paint more than your screen can refresh. So most screens are 60 FPS, but high performance devices, a lot of phones, newer laptops might render at 120. Request animation frame is the way that we're going to do this infinite loop. This is how we're going to make our main loop in JavaScript. You can give it a function and it'll call you back, and then it'll only call you back once. So it doesn't do like set interval. You don't give it a function and it'll call it repeatedly. You give it a function, and then that'll schedule that function to be called at the next paint. That works pretty well. As long as you just keep rescheduling yourself, then you can keep painting along and along, and that's how we get our infinite loop. So yeah, that's enough talking. Let's actually code it maybe. So real briefly, I made just kind of a quick project here with like a few things, very vanilla. So let's walk through this project real quick, and then we'll jump into how to do request animation frame. So if you watch my last stream, I'm a big fan of Parcel. It's a great way to get stuff up and running really quick. It's kind of a magical all-in-one bundler that'll get you going really fast. So Parcel, I can say, Parcel, hey, this is my index, go ahead and serve it. And it knows about TypeScript. And it'll go and use my tsconfig and do all the things that it needs to do for TypeScript. All I need to do here for Parcel is I need to tell it it's a type module, and then I give it the TypeScript file, and it'll go and figure it out. And in fact, I have it running right here. Oh, you know what? I wasn't showing you the code. Let's go show you the code. So I have a script file here in my index.html that starts from here. Index.html. All I have to tell it is it's a type module. I can give it a TypeScript file instead of like a JavaScript file, and then, bam, it'll work, just like that. So let's look into this project a little bit. In this project, I made a few things. First up, I'm using like the built-in canvas, the 2D canvas. So last stream we were playing with WebGPU, and I encourage you to check that out. I have that up on YouTube if you want to check that out. But today we're doing the boring 2D API. So, you know, what I wound up doing is creating a canvas element, putting it into the body of the document, setting a width and height here on canvas, grabbing the 2D context out of there, and I have pixel art here. So I wanted image smoothing true, or set to false. So if I set this to true here, we can show you what that looks like. We'll go over the browser here. I don't know if that shows up pretty, let me zoom in, enhance. Yeah, there we go. Nice and zoomed in. You'll see it's kind of blurry in there. It's the aliasing. And if I go back and set that back to false, you know, we got that kind of crisp pixel art that we know and love. I wrote a clear function. This is just for clearing the screen. Quick init to new up some useful things. Not really important, mostly just like getting keyboard information and defining that sprite that we're drawing. And that sprite is over here. So we got, you know, multiple possible frames of animation. I'm just grabbing just a single slice, and you know, what we do there is we take, okay, I want the index number 3, which winds up being the 4th one. So, you know, 1, 2, 3, 4. You know, we can tell that the 4th one here is the one that we're displaying here. There it is. And that's all that this guy does, is wrap up that that 4th sprite, grabs the X, Y, width, and height to make that, just encapsulate that behavior, and, you know, draw it to the screen where we want it. So, you know, and if you want to check out that code again, I've posted the code up in the chat. But yeah, so that's the init. And last stream we talked about loading, and it's the same here. So we're just loading that image here. We're gonna do some updating later on, and you know, we're gonna draw stuff, and here is where it all gets put together. And you know, you'll notice right now that we do not have an infinite loop, so this doesn't respond to keyboard input. It doesn't do anything other than draw once. You know, we just get this guy once on the screen, and that's it. But we would like him to move and be more game-like. So let's start in on that. So, okay. And, you know, if there's any questions about, you know, the setup here, let me know. But it's, you know, I tried to not do too much, but I did a little bit. Just so that we can get bootstrapped and get going. So Mainloops. So we talked about what they are, and now we're going to make one. You know, how do we make one? Well, in the browser, we use something called request animation frame. So request animation frame schedules us for another callback. So we can just get that started here right now. So let's try it. So I'm just going to make a function called mainloop here. We're going to move all the things that I want to update every frame. So that's our update, where we're going to, you know, pull our input, update our game, do whatever logic every frame that we need to do. We're going to clear the screen and redraw it. So that's the idea. So our main loop here, in order to be like an infinite loop, all we need to do is, to get started here, is do request animation frame, and then we can pass it a main loop. Huzzah! That was easy. Now we have an infinite loop. And it's not being called yet, so it's not starting. But if I were to do this, then we're off to the races. So now we have a main loop. That's basically it. We've got it running. there's a few more features I think that we're going to want here in our main loop, other than just this. I think we're going to want to be able to stop it. One thing that you can do here is, you might have a, game is running. If the game is not running, or if you want to set that running to false, you can have it exit out here, so we won't reschedule our callback. So if we're not running, we're just going to return here out of our main loop. So that allows us to stop. Let's go look at that in the browser here. Let's go play around with that in the browser console. Here we go. So we should be able to set a breakpoint in here. And keep stepping, and we keep coming back. So proof positive that we have a infinite loop using request animation frame. So if we wanted to stop this loop, we could say false here, and that would kick us out of the loop. So now we're not hitting that breakpoint anymore. Cool. So we can now stop our game. We might want to you might have a pause menu, or you might do something like, if there's an error, you might stop the game just to prevent any weird runaway situations, anything like that. Now there's a few other things that I think we're going to want to do in our main loop here. I think we're going to want to keep track of our elapsed time. I think this is useful for time-based movement. So we were talking about earlier, in the Nintendo, when you were updating every frame in a Nintendo, you might have just known how fast the Nintendo was, and then you would move your character every frame 1 or 2 pixels to the right or left, when a D-pad is pressed or something. So that works if you know your hardware, and your hardware is always going to run at a certain speed, but people's machines are all different now. So a lot of times what people do is you keep track of how much time's elapsed in between frames, so that you can scale your movement based on how much time has elapsed. So for example, say I have a really awful machine, like my old one over there. I have a really awful machine, and it's running 10 FPS. I want the game to play the same on a 10 FPS machine as it does on 60 FPS. I want the game to still work. So if I have fewer frames, on the 10 FPS game or the 10 FPS system, I can't do that update by 5 pixels every frame, because that's not going to be the same as a 60 FPS system, where I'm going to update, many more times, 4 times as much. So I can't just do pixels. So we're going to need to do some time-based movement. So the general trick for that is, to use time-based movement using how much time has elapsed. So what I wind up doing here is I'll do last time. So I want to keep track of, last time my loop ran. So I like to just grab performance done now, just to initialize it with something. And then what I'll do here, after I've rescheduled our callback, so we're, after we've decided, okay, we're going to continue the main loop, I want to get elapsed. And I like putting the unit in there, because if you're looking at, I can't tell you how many times I've looked at my own code and I've been elapsed. Is this seconds? Is this milliseconds? Is it microseconds? You just don't know. One really cool thing that happens when you call request animation frame, it calls you back with the now timestamp. So you can use that. in your now. So to get our elapsed time, we take the now timestamp in milliseconds and minus last time. And then we have our elapsed time. And what we can do is we can pass that into our update, which we haven't built yet, but we'll get there. And we can use that to make time-based movement. So we'll do that in a second. We need to update this guy, and I'll just use last time. And then the critical thing to not forget, which I forget all the time, is we need to update last time to now. So every frame we go through here, we're going to say, okay, we're going to get our elapsed. We're going to go ahead and set last time, and the next time through, last time will be the last time, last frame, and then we'll do now, and then we'll just continue like that. We'll go one frame at a time. So let's go ahead and add the code we need to actually do that movement so we can see our little robot guy move across the screen. So let's do that so we can prove to ourselves that the time-based movement is working. So I'm going to go up here to where I define my sprite. I'm going to go sprite x equals 0, sprite y equals 0. And these are just the positions on the screen. Actually, I'm going to do 100 because I don't want to start at 0. I want to start in the middle of the screen. And then I'm going to also set the velocity. So the velocity x, we'll do 100. I like pixels per second. So I like my units in pixels per second. That's usually what I do because I think it's easier to think about. Because pixels per millisecond I have a hard time thinking about. So I like pixels per second, but whatever floats your boat. You can use whatever unit you want. I know a lot of game engines use like meters, kilograms, second. Those are really tough for me. Like if I'm looking at what does a meter, kilogram, or a second mean when I'm looking at this, I don't know. but some people like it. So some people go with that. So teach your own. If it works for you, use it. So right now we're drawing just to the same place every time. So I'm going to go ahead and draw to the new place that I want. Cool. And it still works. Nothing's changed because we're not doing anything with it. But let's do this without time-based movement real quick, and just so I can show you what it looks like. So every frame, we're going to go and update our X, and we're going to update it by 10 pixels. We're going to update our Y, and we're going to update that by 10 pixels. And we can go take a look at that. And he just kind of rockets off the screen. I'm just going to not update the Y. So, cool. Now that we're doing that 10, what does that 10 mean? That means we're updating 10 pixels to the right every frame. So right now I'm running at theoretically 60 FPS on the screen. What that means is every frame I'm updating 10 pixels. And if I were on a machine like 30 FPS, I would be updating half as far. So we don't want that. So we want to fix that. So let's go ahead and grab our sprite x velocity, and we'll convert this elapsed to seconds, which is elapsed divided by 1,000 milliseconds in a second. So we'll go and take that and multiply it by seconds. So if our velocity is in pixels per second and we multiply by seconds, that the seconds cancel out and we're left with just pixels. And we're going to update by that many pixels every frame. Cool. So if I go over here and we can take a look at it, we can see that, oh yeah, okay, that certainly looks like 100 pixels per second to me in the X and Y direction. Let's make the Y not move. So I can kind of grok that. The screen is about 600 pixels wide, so takes about, it starts about 100 over, so it takes about 5 seconds to get across the screen. That makes sense. So that's tracking, right? That makes sense. Why we want to do time-based movement. And this is kind of your table stakes. Like, honestly, you can get pretty far just with this. So, if you didn't go to like limiting FPS, or you didn't go any further, you can get pretty far with this. And this is like basic. This is if you were to give this a name, this type of update, this is like super basic Euler integration. If you hear some fancy game dev talk and you're like, oh, they're talking about like integrating positions or integrating our integrator, all it is we're updating our position over time, and then there's different techniques, and this is called Euler. And there's different techniques. There's like a popular one is Verlet, to use Verlet, and then there's modified Eulers that have different properties, other terms you might have in here. If you have acceleration, you might add, sprite, acceleration x times seconds per second. You might have a more nuanced integration. But, depending on the reason you might want to use a different integrator is a lot of times depends on your use case. So like if you need super accurate like paths, like trajectories, like you might use Verlet over Euler, because Euler is known to not accurately trace a real trajectory as accurately as like Verlet. They're both still approximations, because keep in mind, we're still doing a step every 16 milliseconds. So we're kind of like, plotting, lines between dots. It's not doing a smooth contiguous arc when we're doing updates like this. It's just a approximation. So that's something to keep in mind when you're doing time-based movement is, okay, what integrator am I using? Do I care? A lot of times you can get away with this. Like, if you need to do like something more, you can take a look at some of the Verlet stuff, and that's usually like where people go next. And it's a lot of times you'll look at that for like physics. Like you have a physics simulation, like you got Angry Birds or something, or you gotta, you need to more accurately model collisions, for whatever reason, or you have a different type of problem that you need to model. You might use a different integrator. So that's time-based movement. And, if that doesn't make sense, let me know, and we can dig into it a little bit more. What I want to do with this is we've kind of like, gummed up our main here with a lot of different like concerns. Like we have this timing concern, we have our update clear and draw kind of interspersed in here. So I kind of want to refactor this into a separate type. I use in Excalibur, I have a type called a clock, and that's what it's responsible for. Its sole purpose is managing the main loop. That way I don't have my main loop concerns interspersed with my order of update or any of those other concerns. It's just a clock. So let's go ahead and let's refactor this real quick before we get on to our next things in our to-dos. So where we're going to talk about like limiting FPS and why you might want to do that. Doing like fixed update FPS, and then related to that, interpolation. So cool. So let's refactor that. I'm going to make a clock. And we're going to go ahead and export class clock. Yay, it's going to have a constructor. What do clocks do? They are going to tick or step. So every step of the clock is one invocation of our main loop. So that's what I'm thinking of. Elapsed milliseconds number. So we'll do that. So that's our clock. So we're gonna give it a callback, which is it's gonna run. So that callback is the thing that does work. So that's what I want. I want my clock to do the thing that call the thing that does work, and get rid of all of this extra junk in here that's kind of like cluttering up the concern. So we'll go ahead and do that. I'm going to go ahead and do my main loop here. It's going to look very similar. So we're going to do main loop, and if this is running, this is not running, we're going to return. I'm going to go ahead and awesome features in VS Code here, where you can just declare properties. Oop, I want Boolean. All right, cool. So, and remember, we're gonna reschedule ourselves. We're gonna request animation frame and call back the main loop. When we're doing it in a class here, it'll lose the this context because it's calling it outside. You're getting called back from the system, so you actually have to bind it to make sure that you don't lose your main, the this context. That's in this case, kind of a bummer. But that's kind of what we have to do. I'm gonna go ahead and same deals we did before. We're gonna grab this elapsed. Maybe I'll just copy this. We'll copy that in, and then I want to generate a last time field. So we're going to keep track of the last time. Ooh, that's not what I wanted. I didn't want a new method. No, get out of here. I want a new property. Nope, it's not going to do it for me. All right. So I want last time. It's a number. And I'm going to do the same thing I did outside here. I'm just going to reinitialize it to performance now. And we're going to fix this up here, and because we're calling it off of this now, class property, we can go ahead and call our step. You pass it our elapsed, and then reset our last time to now. Cool. So then we got our main loop kind of in a clock type. I'm going to add a couple little helpers here to get us started. So I want to be able to start the clock. So we're going to start the clock, and we're going to kick off our main loop. Performance now. So that'll get us going. So that'll kick off that. This will be like the first initial kick, and then this will be an infinite loop as long as it's running. Otherwise, if it's not running, we get kicked out and we exit. And then I'm going to add a stop, because that's useful. And all we have to do is say that's false, and then we won't reschedule ourselves. Easy like that. We can stop and start it all as much as we want. And it's A-okay. So let's go over here and add that refactoring back in. So I'm going to go ahead and define my clock out here. So we're going to new up our clock. And then we're going to, you know what I'm going to do? Is I'm going to just have a reference out here because I'm going to want to reference it later. So I'm going to new up our clock. And our clock takes a step function, and it passes back elapsed milliseconds. So all we need now is just to move this into our clock, and then we can delete all of this. Delete. More deleting. Excellent. Format. Awesome. Cool. And that looks a lot nicer. And we're going to have to start the clock. That looks a lot nicer. And, we can go back and look at the browser, and we can see that everything still works. And we have a nice little clock. And now we're not muddying up our concerns there with all of that extra logic. And now it's wrapped up real nice. So we don't have to think about, okay, what is all this extra goo that I don't want to mess up because I'll be sad and my game won't work if I mess it up. Cool. One thing that I'm gonna want to do is I'm gonna want to measure the FPS of the clock directly, and I stole this type from Excalibur, but this is uh, something I use to measure FPS. If you're curious, you can go and steal it yourself. But what this does is it actually counts. It takes the time and counts how many frames you do, and then it'll report back the FPS. So you can go ahead and steal this type 2 if you want. But this is just kind of a quick way if you want to measure FPS exactly. So I actually want to put this into the clock so that I can measure the actual FPS of the clock. So we're going to go ahead and do that. So I'm going to make a public FPS sampler equals new FPS sampler. And it has a couple options. You have to give it a initial FPS to start at. So I'm just going to give it 60. And then you have to give it how does it get the current time, which we're just going to use performance.now. So once you've got that, in order to use the sampler, we just have to tell it when it starts and when it ends, when the frame ends. So I'm going to say that the start is at the start there, and this is the end. Cool. Easy peasy. And then I want to draw that. To the screen so that we can see that the FPS is actually updating. So we can do that in our draw here. I'm going to move our clock a little further up. So then in our draw, we can do context dot fill text clock FPS to fixed, because it's going to be like a huge decimal number, and we're going to we're just going to stick it there. And then I'm going to let's see, what is it, text style? Style, font, it's font. So we're just going to make it a big sans serif text, whatever my system is, and then we're going to make it yellow. And that's any CSS color there. And this is just a CSS string. So we can go back to the browser here, and we can see, so we are at 60 FPS. It's sampling our FPS, and we can see that we got 60 FPS. Huzzah! That works. And so that'll be important when we start doing some cooler stuff in a bit, where we start messing with FPS. But this is actually measuring the actual FPS of request animation frame on my system. So you notice that we bounce around 60 here a little bit, but we are staying roughly in 60. So pretty cool. I think this is a cool way to actually measure it, and not necessarily rely on the math necessarily. That okay, well, it should be this, but to actually measure it makes you feel good about it. Cool. So let's go and see what we got next. So that was time-based movement and doing FPS. So sometimes you might want to limit your FPS. So for various reasons, you might be going for a particular style. You might be going for, well, I know the game works at 30 FPS, so we're going to limit it to 30 FPS. We're going to artificially lower the speed at which we draw, and that might be for performance reasons. So, for example, it's been the case for me where you get to a system that can run at a higher frame rate, but you got inconsistent frame rate. So, say you're on a system that can do 120, but your game is bouncing between 45 and 120, and that really sucks to play. When your frame rate is not consistent in a game, it can really hurt the feeling and the play of your game. So you might be well, we could fix this, certainly, given enough time, or we could, it's acceptable, at 30 frames, and the game is always acceptable at 30 frames. So we're just going to limit the FPS to that. So people have a consistent experience. The person that's got the high-end machine has a consistent experience. The person on low-end machine has a consistent experience. Those are reasons that you might do it. And that may be because you have some, performance issues, like, that you'd love to fix, or maybe you're hitting a hard barrier and you can't fix it for whatever reason. Maybe it's your engine, maybe it's something else, like an algorithm that is running, you can't run it at 120 hertz, and it's just tanking the browser, or, another reason you might want to do it is maybe you have a game that's like low action, like there's not a lot going on, and you want to save battery. So that's a positive angle. So like if you're running like at a lower frame rate, you don't need to chew up as much battery. So if you're on a mobile game or a battery constrained device, that might be a reason to limit FPS, is you don't want to chew through battery. So those are all good reasons to limit FPS. It's not a like a more is better kind of a situation. So yeah, so let's look at how you might do that. And you might be guessing that we're going to go to the clock. So let's go take a look at that clock. So what do we want to do here? Well, we want to set a maximum FPS. So given the current game, I don't want to go over this FPS. How do we do that? Well, I'm going to go ahead and make a cursed optional variable here. We're going to give it max FPS, and by default it's going to be infinity. So like, which is kind of nice, because you can say like, oh, by default it's just going to go as fast as the system can go. So I think infinity is a great value, and that's just something we can use in JavaScript. We can just throw down infinity there, and that's a valid value for it to be. So that works. So what we want to do is, if we are going to update and we're going to update too fast, we want to skip a frame. So how do we do that? So we can calculate the interval of the max FPS by taking that. I'm gonna go ahead and make this available to me as a member. We can take that. Remember that 1,000 trick I talked about earlier. You can convert anything that is an FPS to milliseconds per frame by putting 1,000 on top of it. So, for example, if you if we're talking about 60 frames per second, if you do 1,000 divided by 60, that's 16.6 repeating milliseconds. So given our max FPS by default of infinity, this is 0, but we'll deal with that in a second. But let's say we were setting our max FPS to 30. So 1,000 divided by 30 FPS, that'll give us 33.3 repeating milliseconds per frame. So what we'll want to do then is, if we're going to update our frame faster than our interval, we're going to want to skip. So we want our elapsed time to be bigger than our target max FPS, or equal to. So this is skip the frame. We don't need that there, but I'm just going to put it there just to make it clear that that's what we're doing. So when we're calling our main loop, this will go as fast as the browser can go. So on my machine right now that we're streaming on, it can do 60 FPS. But if I want 30 FPS, what'll happen is it'll be like, okay, I'm going to go and I'm going to enter in here and be like, okay, I'm going to go enter this block once, and then in the next frame, I'm going to skip this. and then I'm going to enter this block once, and then I'm going to skip. So, because, it's evenly divisible there. So what will wind up happening is we'll artificially run at 30 FPS by skipping frames. And that's how we do it. And then, like, if you wanted to tweak it, like, into a non-divisible one, you'll have, like, we'll run a couple frames, and then we'll skip a few, and then we'll run, and we'll skip in different patterns. So, okay, so hopefully that makes sense. And if it doesn't, or I've made a tremendous error, please say so in the chat. But that's generally how we do it, is we artificially skip frames if we're looping too quickly. Cool. So we're going to keep track of our leftovers so that in the case of something that's not evenly divisible, we can shift to the right number. So what I'm going to wind up doing here is if our FPS interval is not 0, because, and by default here, this infinity, if you divide anything by infinity in JavaScript, it'll come out as 0. So like if let's make this a little bigger, up at the top right here. So if I did 1,000 divided by infinity, that's a 0. So we want to account for that 0. Otherwise we'll be real sad if we don't. This is very similar to code that I have in Excalibur right now. So this is actually production code. And if you find a problem with it, if you take issue with it, let me know, because then we'll fix it. Open a bug, and then we'll fix it. So I'm going to go ahead and do this thing. So what am I doing here is I'm doing a mod of our elapsed milliseconds, and mod is just a remainder. So I'm dividing elapsed by FPS interval and getting the remainder. So for example, if I had if I was constraining to 30 FPS, I'm going to have, and my machine is 60 FPS, I'm going to have 33 seconds of leftovers. And that'll align me to the right amount. What I'll need to do is something a little hokey pokey here, is I'll need to back up the clock. I'll make this not const. I'll need to back up our clock in order to set the simulation straight, to account for the leftovers. So when we're, what I should do is I should move this into our block, because we only want to step if we're in this block. So I need to back up our leftovers here to actually pass the right elapsed time to the simulation. So keep in mind right here is if we are, if we elapsed at 16 milliseconds, or we elapsed it longer than the interval, we're going to pass the wrong interval to the simulation. So we need to actually subtract that back out, so that the simulation thinks that we're running at the right FPS, at our 30 FPS. So I know that didn't make a lot of sense maybe, but trust me, we need to back up our leftovers back into the simulation so that we're actually constraining the simulation to the right time period. And then the last thing I do here is handle the 0 case again. There's probably a more elegant way to do this, but this is what I wind up doing. So in the case of 0, we also need to back up our leftovers again. Else we're going to go ahead and just do the normal thing. So this is the non-infinity case. So non-infinity case, we're going to go ahead and do, which is the usual case. We're going to go ahead and back things up. And then we want to run our sampler end. You'll notice I have the sampler end inside of the frame that we actually run. That's on purpose because I don't want to, because we didn't actually run the frame if we're skipping. So I don't want to sample the end of that, but I do want to sample the start. So cool. So we're going to do that. And then now that we have that, we should be able to tell our clock that we want to run at like 30 FPS. So let's go over there and go to our clock here and give it like 30 FPS. And then huzzah! Look at that. We're running at 30 FPS. Let's refresh that. Very cool. Did that kind of track? That's so now the whole game is running at 30 FPS. Game loosely defined. This whole main loop is running at 30 FPS. That's more accurate, perhaps. Cool. So that was cool and nifty. What do we want to do next? Here, let's go take a look at our to-dos. So we figured out limiting FPS, and then we talked about some of the reasons you might want to do that. You want to conserve battery. Your game doesn't consistently perform at higher levels. You have high variability in your frame rate. You have a performance issue you can't overcome, that kind of stuff. Now there is also a nuanced situation here where you want to run your physics. So this next bullet point that I want to talk about is called fixed updates. So you might want to always force the update of your game to run at a fixed FPS. And there's just let your graphics run at whatever they're going to run. So, you might say your graphics are like, they're unconstrained. You might have your graphics unconstrained, and you might say, okay, graphics are going to run however fast they need to go, but I'm going to only run my physics at 60 FPS, and I want to guarantee it no matter what system they've got. Even if they're running at like 20 frames per second visually, I need to run the physics at 60 frames. And the reasons you might want to do that are like, you want predictable physics. So one problem with this, this simulation that we're talking about right now, it's still not deterministic because of the different browser frame rates. So you might, even within a certain, even on the same machine, you might have you might have like a billion tabs open. You might have, a program running in the background. You might be playing, you might have a game running on the other tab or the other screen. That can tank the FPS of your game, and you might update through a wall, and your physics won't be deterministic from individual, multiple different playthroughs on the same machine. Even if your machine can do 60 FPS consistently, if you start dropping frames, your update distance, we did time-based movement, sure, but your update distance gets bigger and bigger the wider your elapsed time goes. So let's take a look at that. If this number gets really big, then every frame you're going to update a big chunk of pixels, across the screen. So if you are standing on a ledge or next to a wall, you might clip through the wall. So one trick to fix this, one of the many tricks to fix this, is to force your physics to always run at a certain FPS. A lot of game engines do this. You can actually, in Unity, I think you can click, fix to update on your physics. I think there are plenty of games that do this. I think Rocket League does fixed update. A lot of games that have where the physics is important to the game, you'll wind up doing a fixed update. So you're, no matter what, the engine will guarantee that you run enough of the simulation, and you are always running 60 FPS of physics, even if the game is suffering. Like even if visually you're like rocking 5 frames, the physics is running consistently across frame rates. So that's one thing that you might want to do. So let's go take a look at that. How do we make that happen? Glad you asked, or I asked. So let's go ahead and take a look at how to do that. So fixed update can happen. Let's go do it in the clock here. We don't really care about doing this extra business with the draw, and we could maybe refactor the clock to handle the update as well. I'm gonna do it in here as well. I'm gonna add another FPS sampler here, just so that we can measure the FPS of the updates. So let's see, sampler, new FPS sampler, and we'll do the same thing we did before, where we just say it's 60, and the now is performance done now. So what we're gonna do here is I'm gonna say, okay, I'm gonna do our sampler, we're gonna go start it, and then we're gonna say while we are lagging behind our fixed update interval in milliseconds, I want to keep updating. And let's go ahead and define these actually. So let me go, I don't need this. I might need this here. I'm just gonna put a lag here, lag milliseconds. So the lag in milliseconds is while we are updating, we're gonna grab the elapsed and we're gonna work down the elapsed. So we start with 0 lag, and if our elapsed time was like, I don't know, 30 milliseconds, we're gonna work down that elapsed time and make sure that we can fit it into our fixed update. So we wanna guarantee a fixed update. So we're gonna work through that entire fixed update and make sure that we update that amount. And then our update is not gonna be elapsed anymore. It's gonna be our fixed update, which I spelled wrong. Fixed update interval milliseconds. And let's say that we want to, our fixed update interval milliseconds, this is gonna be whatever FPS we want our physics to always run at. And let's pick like a non-obvious number. Let's say we always want it to be 50 FPS. So, so we'll do like 50 FPS for the physics update. So what we'll do is we'll work down that lag. And then we'll end our sampler because we're actually doing our update. Cool. So this will make it happen. So we're going to go ahead and do our, so as you can see in here, we'll do potentially multiple updates. So like say, we have our physics set to 50 here. This is set to 30. We'll need to do multiple updates per draw potentially. So that's what's going to happen here. So I'll go ahead and save that. And let me go ahead and add another little draw for our text here so we can get the physics update. And we'll make the physics like, I don't know, we'll make it green. So, and I'll make this, I'll just add this a little label here so we'll know what it is. So we'll call this draw FPS, and then we'll do, we'll call this one update FPS. Cool, and then we gotta move this down to here. Green is a bad color. Let me pick a different one. Okay. Cool. So now, let's see. Now we are getting, okay, so it's still saying 30. Why is it saying 30? Shouldn't be saying 30. Okay, I did something wrong. Let's see. Let's look at the code. So, oh, I know what we did. I need to keep track of our lag differently because I'm updating fixed update interval. I'm working through our lag. Oh, shoot, I'm losing it. So this needs to stay around each frame. Otherwise, we'll be we'll be sad because we won't work through the difference between frames. So that's what it was. I didn't do it plus equals. Cool. So remember, we have our draw set to 30 FPS, and now our update is set at a fixed update of 50. So awesome. We got that working. Now there's one problem with fixed updates. So let me switch this around a little bit. I'm going to switch our draw back to 60, and I'm going to switch our fixed update to like something really rough, like 5. This is an extreme example, but it kind of shows the problem when you start, having disparate draw FPS and fixed update FPS. So, for example, it might be totally reasonable for you to have like fixed update for your physics at 50 FPS or 60, and then you're on an awesome machine that can do draws at 120 FPS. Well, this same problem exists there. So we're going to need to figure out how to solve that. And what a lot of people do, what a lot of people wind up doing is something called interpolation. So to smooth that out so that it doesn't look so chunky, this is an extreme example. Obviously you don't want to run your game at 5 FPS. But just so that we can see it, see the problem, I'm having it at 5 FPS. But you'll want to interpolate between those frames and lie. Good game dev is all about tricking your users into thinking it's working. You'll want to lie and interpolate in between those frames so that you're still taking advantage of all the frames that you can draw. Like we got 60 frames we can draw. It shouldn't look that chunky. Or if you're on 120 hertz, you got a lot of frames to draw. So that's where interpolation comes in. So let's take a look at that. How do we do interpolation? So there's a couple ways to do this. There's something called predictive interpolation, where you predict where your sprite's going to go in the future, and you interpolate that way. That can have some jarring artifacts. Sometimes it can be good, but if you do predictive interpolation and you're wrong about where it's going to land, then it'll look weird. The other way to do it is to interpolate between the last frame and the new frame, and that works pretty well. You get some rounded trajectories, but it still works pretty well. So how do we do that? So a big way to, an easy way to do that is to capture the old position when you're updating. So let's go ahead and grab that. Let's go grab the sprite x old. I'm going to call it sprite, or old sprite x is what I'm going to call it. Old sprite x. So we're going to, before we update our sprite position, we're going to go ahead and grab it. So we got sprite x and sprite y. We're going to go ahead and grab it. And what we're going to do with that is we're going to go into the draw here, and we're going to go and figure out how much we're lagging and interpolate between how far along we are in the lag and where we need to where we need to like where we need to go when we're done with our lag. So how do we do that? So I'm just going to define a lerp function. So we're going to say a to b in a time. So let's think about how lerps work. And I'm going to write a lerp in a weird way that you don't normally see it, but I think it's the same. I'm pretty sure it's the same. But when time is 0, I'm going to make this actually the word time. When time is 0, you want all A, and when time is 1, you want all B. So you're the way that generally you do this is like, time is between 0 and 1. So if at time 0 I want all A, I need to do 1 minus time, right? Because that would be 1 times A. So that would just be A. But at time 1, I want all B. That would just be B times time, right? And that's a lerp, right? So we're going to lerp between two values, between A and B, over a certain amount of time. So we're going to have a blend factor, and I'll get to that in a second. So it's going to be something. We'll have some blend. I'll just make it 0 right now. We'll have some blend value. But then we're going to have our new x is going to be the lerp of, it's going to be old sprite x, old sprite. Is that not? Did I not define it in the right spot? Oh, I put it here. I need it up here too. So we'll do that real quick. Boop. Old. Cool. And we'll start it at 100. So old sprite x, and then sprite x, which is our destination, and then we're gonna have some blend, and then we'll do new y is the old y and the new y, and with some blend. So okay, so what's our blend value? How do we figure out our blend? This is done with grabbing the that lag that we have. We're calculating every frame. We're going to figure out how much we're lagging. We're going to squirrel that away. So we're going to go current frame lag. We're going to grab that lag in milliseconds. I'm going to put this somewhere I can grab it in the draw. I'm just going to start at 0. This we'll assume that we're not lagging. I'm going to need to move this up too. We're going to assume we're not lagging. We're going to grab that every time we finish. So we've worked through a lot of our lag here. So we've done all our updates that we're going to do. And then we have some lag left over. We're going to take that leftover lag and figure out how much of the frame that we're through. So what does that look like? It just looks like this. Current frame lag divided by fixed interval update. And remember, that's the interval that we're updating. So we had that one update that we couldn't finish, or however much update that we couldn't finish. We're going to go ahead and interpolate over that. And that will be our lerp. And let's see if that works. Oh, I didn't update this. New x and new y. All right, I got it. It's broken, but it's something interesting. So let me refresh this. So it's kind of working, but it's kind of not. So what I'm pretty sure is happening is our old sprite x and y are not updating properly. So it's not what it expects it to be. So let's see, what is wrong here? Let's take a look at the code. Exciting when I don't get it right. All right, so let's take a look at this. So we are interpolating properly. Okay, we're blending properly. Get rid of this. We got our blend here. We got our new sprite. X new Y. Oh, I'm shadowing it. Okay. That's what happens when you shadow a variable. Okay, so now we can see that it's working. So pretty cool. So our update is looking pretty smooth now that we're doing interpolation. Even though our update is only running at 5 FPS, that's pretty cool, you know? That's pretty sick, right? We're lying so well right now using that interpolation. And the nice thing about using this like looking back interpolation instead of like looking forward is you don't get weird artifacts if you move like the keyboard around. And we can play with that if we want, like real quick. Let's just do that with the keyboard. So if keyboard is pressed, arrow right, then sprite x velocity equals 100. Oop, that's not what I want. And we'll do left. I'm just going to set these to 0 when we start. And then we're going to need up and down. Negative y is up in this situation. Cool. Oh, that needs to be down. Cool. All right, let's take a look at that. Hey, thanks, Chris. It does look nice. There we go. And we're updating on the keyboard, and I can definitely feel the 5 FPS on the update, but it looks nice. Versus like if I take the lerp off, like we'll be able to see like the 5 FPS without, let's take the lerp off here real quick and just do sprite X and sprite Y. And go take a look at what that looks like. Yeah, little rough without the learning interpolation there, you know, with that interpolation doesn't look so nice. So if I turn the interpolation back on, even though our update's running at 5, you know, again, 5 is just to illustrate the problem. You know, like the situation that we're really running into here is like when your draw and your update are very disproportionate. And the reason that you would set a fixed update like this is so that your physics is deterministic and your simulation is deterministic. So what does that mean? That means it just is always the same. You know, it always behaves exactly the same, no matter what the machine is doing. So, you know, I can even say like in here, you know, I'm putting in like FPSs that are less than what my machine can do, but we can do something that, you know, we can go to like 120 here. You know, I can run the physics update. Like if I want my physics to be super high fidelity, like I want to make sure that there's like a lot of physics frames going, I can set this to super high. Like you don't just have to set it low. Like you can be like, okay, the physics is the most important part of this game. I need that to be buttery smooth. You know, I need my integration to be super precise. And that's one advantage here that we didn't really talk about, is that even with Euler integration, kind of the basic Euler style integration that I'm doing in the update here, super basic Euler style integration, right? I'm doing smaller steps now, so this is more accurate. So this is super big for like if you're doing like, you know, collisions, you're doing like physics and stuff like that. Like the more, you know, the smaller iterations you can do, the more precise your simulation is, and a lot of times the more stable it is. This comes at a cost though, because you have to run all of those frames, right? Like it's not free. But there is probably a healthy middle there where you can pick one that works really well for you. So awesome. So that's all I had for today. And I'm right at where I wanted to be. So I'm going to go ahead and like check in this code. Implement FPS shenanigans. Shenanigans. Sure, we'll go ahead and do that. Whoa, that was loud. So we'll go ahead and do that and push that up, and I'll repaste the repo here for anyone that wants to check it out. You know, quick aside. All of this stuff is in Excalibur, so this is all like Excalibur stuff. So it's all built in there. So if you want to check out excaliburjs.com or github.com/excaliburjs, that'd be awesome. But all of this stuff is built in there. And even if you're not using Excalibur, a lot of other like, you know, game frameworks like Pygame or other game frameworks, like this stuff all applies. So like it doesn't have to be, this is not just browser specific. Like whatever you're doing can apply in anything that you're using. So like if you're using Unity, now you know what these things mean, like, or why you might want them. Or using Unreal, you might know why you might want to turn on certain settings in like your physics engine or whatever you're using. In Godot, you might want to do whatever you might want to adjust your FPS or your fixed update or your interpolation, and you know what they do now. So hey, that's pretty cool. So those are reasons to do that. And yeah. Otherwise, I think it's going to be an early one today. Only an hour and change today. This time I knew what I was talking about, more or less, instead of like learning WebGPU on the fly. But if you want to check that out, that WebGPU is posted up on YouTube as well. And this one will be up on YouTube soon-ish, no promises. So, but yeah, if you'd like to support me, you can check out my sponsors or my Patreon. That would be really awesome. If you'd like to check out Excalibur.js, also super awesome. You can also take a look at it. We have a lot of code and a lot of contributors. Some of the contributors are on the stream right now. Thank you. Yeah, very cool. Well, I'm going to call it there tonight. I really appreciate it. All you sticking around and listening to me talk about Mainloops for an hour and change. But that'll be it. Thanks again.